Now, in this lecture, we find out the area of the green semicircle using two different methods. In the drawing, we have two semicircles. We know that line segment AC equals to 5 units in its length. This is line segment CB that is equals to 1 unit in its length. And our mission is to find out the area of this green semicircle. Okay, so first of all, we join points P and B together by a straight line. The next step, I'll copy the white semicircle and we'll implement all 7 on the white semicircle. Actually, by joining points P and B together by a straight line, we create a peripheral angle APB. So I'll copy the white angle, I'll copy the white semicircle and we'll implement rule 7 with the white semicircle. Side AB total equals to 5 plus 1, that is 6. Again, AB equals to 6 units in its length. So actually, this is the white semicircle that they call it from the original drawing. AB is the diameter of this semicircle, so I write it down. AB is the diameter of the white semicircle. You know that it is equals to 6 units in its length. By joining points P and B together by a straight line, we created peripheral angle APB. This is peripheral angle APB, and peripheral angle APB is subtended on AB, that is the diameter of this semicircle, and therefore we can implement here rule 7. Repeat again, this is peripheral angle APB, that is subtended on AB, that is the diameter of this semicircle, and therefore we can implement here rule 7. I'll repeat quickly on rule 7. According to rule 7, if a peripheral angle is subtended on the diameter of the circle, then it is equals to 90 degrees. So here we have a circle, and we know that AB is the diameter of this circle, and we have peripheral angle ACB that is subtended on AB, that is the diameter of this circle, and therefore according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. Why? Because in our drawing we have peripheral angle APB that is subtended on AB, that is the diameter of the semicircle, and therefore according to rule 7, peripheral angle APB must be equal to 90 degrees in its size. So angle, this angle APB is a right angle according to rule 7. So it is not actually found out the peripheral angle APB is equal to 90 degrees in its size according to rule 7. In the next step, we join points P and C together by a straight line. And I'll copy the green semicircle in the new page, and we will implement rule 7 on the green semicircle. Side AC equals to 5 units in its length. So actually, this is the green semicircle that I covered from the original drawing. By joining points P and C together by a straight line, we created the peripheral angle ACP. This is peripheral angle ACP. And in this green semicircle, we know that AP is the diameter of the green semicircle. And it is very easy to see that peripheral angle ACP is subtended on AP, that is the diameter of this semicircle. And therefore, according to rule 7, peripheral angle ACP equals to 90 degrees in its size. So I write down peripheral angle ACP equals to 90 degrees in its size according to the same rule, rule 7. Okay. So this angle is the right angle according to rule 7. So in the drawing it is very easy to see that this angle is a common angle. It belongs to both triangles. It belongs to the green right angle APC, and this angle A, it is also belongs to the right triangle APB. Therefore, this angle A is a common angle. Okay, so we define this common angle as alpha. And in the right green triangle APC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the missing third angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Okay, likewise, so this is angle alpha, it is a common angle that belongs also to this right angle, triangle APB. So this angle equals to alpha. So the right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the missing third angle must be equal to 90 degrees minus alpha. So in the next step, I'll copy this green white triangle APB and this green triangle APC in the new page, and we'll prove that those two right angles are similar to each other according to angle similarity rule. Again, side AB equals to 6 units in its length. So I copied the right triangle APB in this new page. Next step, we'll copy the right green triangle APB in the same page, and we'll prove that those two right triangles are similar to each other according to angle similarity rule. Side AC equals to 5 units in its length according to what is given us in the question. So actually, those are the two right triangles that I copied from the original drawing. In the next step, I prove that those two right triangles are similar to each other according to angle similarity rule. So we prove that the right triangle APB is similar to the right green triangle, triangle APC. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle APB in the right triangle, APB, and it is equal to this angle, that is actually angle ACP in the green triangle. I repeat again, I actually found out that angle APB in the right angle equals to angle ACP in the green triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles, they are both equal to alpha, therefore they are equal to each other. So really, this is angle PAB, the right angle, and it is equal to this angle. This is actually angle PAC, the green triangle. Repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Okay, angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle ABP in the right angle, APB, and it is equal to this angle. This is actually angle APC in the right triangle APC. Repeat again. Angle ABP in the right triangle APB equals to angle APC in the right triangle APC. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually found out that all the triangles, the right triangle APC, are correspondingly equal to all the triangles in the right triangle APB. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. Actually found out that the right green triangle APC is similar, this is the sign of similar, to the right triangle APB, according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AC, the green triangle, over side AP in the white triangle equals to side AP in the green triangle over side AB in the white triangle. I'll repeat again. We derive that side AC in the green triangle over side AP in the white triangle equals to side AP in the green triangle over side AB in the white triangle. Okay. AC equals to 5 units in its length, therefore we substitute AC by 5 over AP. AP is the missing side, so we leave it as it is. And it is equals to AP, again AP is the missing side, so we leave it as it is, over AB. AB equals to 6, so we substitute AB by 6. So in conclusion, we actually found out that five over AP equals to AP over 6. Here we cross multiply this equation, and we get that 5 times 6 is 30, so 30 equals to AP squared. 30 equals to AP squared. Here we take a root out of this equation, and finally we get that the missing side AP equals to the square root of 30 units. AP equals to the square root of 3 units in its life, to the square root of 30 units in its life. This is the missing side AP. This is actually the diameter of this green semicircle, and it's equals to square root of 30 units in its length. AP is the diameter of the green semicircle. If AP is the diameter, it means that AP over 2 is the radius of the green semicircle. So the radius of the green semicircle R equals to the diameter AP over 2. AP is square root of 30. AP over 2 is square root of 30 over 2. So actually found out in conclusion that the radius of the green semicircle equals to the square root of 30 units in its length. And the area of this green semicircle equals to pi r squared, that is the area of the circle, over 2. Again, the area of this green semicircle equals to pi r squared over 2. So I write it down. The area of the green semicircle, that is the area that we are looking for in this question, equals to pi r squared over 2. So it is pi, r is square root of 30, so it is square root of 30 squared over 2. So here, the area of the green semicircle equals to pi, so here we have the radius equals to 30 equals to AP squared, therefore AP equals to the square root of 30, and the radius is AP over 2. So the radius equals to the square root of 30 over 2. Therefore the radius is square root of 30 over 2. The radius equals to the square root of 30 over 2. Therefore the area of the green semicircle equals to pi r squared over 2. So it is pi times square root of 30 over 2 squared divided by 2. So the area of the green semicircle in total must be equal to pi, and square root of 30 squared is 30 over 2 squared. 2 squared is 4, so it is 30 over 4 over 2. 30 over 4 over 2 is 30 times 2 times 4. 30 over 2 times 4. And here we have 30 over 2 is 15. So in total this expression equals to 15 pi over 4 square units. 15 over 4 is 3.75. And therefore this expression equals to 3.75 pi square units. So if we found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, this equals to 11.78 square units. Okay, repeat again. Actually found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. So we finished with the first method. In the next step, I'll present to you how to find out the area of this green semicircle according to the second method. The second method, we join points P and B together by a straight line. And I'll copy the white semicircle in the new page, and we'll analyze the white semicircle. Actually, we'll implement all 7 on the white semicircle exactly as we did in the first method. Here, AB in total equals to 5 plus 1, that is 6. So actually, this is the white semicircle that I copied from the original drawing. Again, AB is the diameter of the white semicircle, so I write it down. AB is the diameter of the white semicircle. Again, by joining points P and B together by a straight line, we created peripheral angle APB. Peripheral angle APB subtended on AB, that is the diameter of the semicircle, and therefore according to rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in its size. Therefore, according to rule 7, this angle equals to 90 degrees in its size. Line segment BP gets 90 degrees with AP. AP is the diameter of the green semicircle. Again, AP is the diameter of the green semicircle. If this is the center of the green semicircle, so we define the center of this green circle as O. Therefore, OP is the radius of the green semicircle. So I copy point O from here to this drawing. Copy point O from the original drawing to this drawing here. So I found out that actually that OP is the radius of the green semicircle. Again, OP is the radius of the green semicircle. So we define the radius of this semicircle as R. Therefore, OP equals to R. Again, OP is the radius of the green semicircle. That is equals to R according to our definition. And we have here line segment PB creates 90 degrees with the radius OP of the green semicircle. Therefore, we can implement here rule 1. I'll put quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have the radius OM that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So whenever you have a straight line, like the straight line AB that creates 90 degrees with the radius MO, it is defined as a tangent. Here, AB is the tangent to this semicircle, to this circle at point M. Okay, and in our drawing, we have line segment BP creates 90 degrees with the radius OP, and therefore, according to rule 1, line segment BP must be defined as a tangent. Why? Because it's creates 90 degrees with the radius. And there you can see that line segment AB creates 90 degrees with the radius OM, and therefore line segment AB is defined is tangent. Therefore, for mole 1, we can conclude that because of the fact that line segment BP creates 90 degrees with the radius PO, it must be tangent. It must be tangent to the green semicircle. So right now we actually found out that line segment BP is defined as a tangent to the green semicircle. So line segment BP is defined as a tangent to the green semicircle. Again, this is line segment BP that is defined as a tangent to the green semicircle. So here we can actually implement rule 10 if we focus on the common external point B. For the common external point B, we have tangent BP to the green semicircle, and from the same common external point B, we extended the common external point B by straight line until we created chord CA. So we have tangent BP and chord CA from point B, that is the common external point B, and therefore we can implement here rule 10. I'll repeat quickly on rule 10. According to rule 10, rule 10 is true in any circle. So in any circle, if AB is a chord, here AB is a chord in this circle, and PT is a tangent to the circle, here PT, this is tangent PT, this is tangent to this circle point T. Then in this domain, the following equation will be true, that PT squared, the tangent PT squared, equals to PA times PB. Again, PT squared equals to PA times PB. We can actually implement rule 10 in our drawing. Why? Because in our drawing, we have from the common external point B, tangent BP to the semicircle, tangent BP, tangent to this green semicircle at point P. And from the same common external point B, we have here the extended point B creates chord AC. Okay, from the same common external point B, we actually extended, we draw a straight line until it cuts the circle at 2 points, A and C. Therefore, all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, we get that PB squared equals to PC times PA. Again, PB squared or BP squared equals to BC times BA. So repeat again, according to rule 10, PB squared, that is the square of the tangent BP, must be equal to BC times BA. Must be equal to BC times BA. According to rule 10. Here, PB squared or BP squared equals to BC times BA according to rule 10. Again, BP squared equals to BC times BA according to rule 10. So the tangent BP is the missing side, so we leave it as it is. This is tangent BP, that is the missing side. And it is equal to, according to rule 10, it is equal to BC. BC is 1, therefore we substitute BC by 1 times BA. BA in total equals to 5 plus 1, that is 6. So BA equals to 6, so we substitute BA by 6. So So for conclusion, we found out that BP squared equals to 1 times 6, that is 6. BP squared equals to 6, we'll take out of this equation, and finally we get that the missing tangent BP is equals to the square root of 6 units in its length. BP equals to the square root of 6 units in its length. In the next step, I'll copy the right triangle APB in the new page, and we'll implement the Pythagoras theorem in the right triangle APB. Again, side PB equals to the square root of 6 units in its length. Side AB equals to 6 units. So this is the right triangle APB as I call it from the original drawing. Here by PT is the evolution for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle APB is AB, therefore the square of the hypotenuse is AB square, and it must be equal to AP square plus PB square. So here we subtract PB square from this equation, and we get that AP squared, the missing side AP squared, equals to AB squared minus PB squared. So the missing side AP squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, minus PB squared. PB is square root of 6, therefore PB squared is square root of 6 squared, that is 6. So in total, we found out that AP squared equals to 36 minus 6 is 30. So AP squared equals to 30. Here we take a root out of this equation. Finally, we get that the missing side AP equals to the square root of 30 units in its length. So actually, this is the missing side AP. This is actually the diameter of the green semicircle. So the diameter of the green semicircle equals to the square root of 30 units in its length. If the diameter of the green semicircle equals to the square root of 30 units in its length, it means that the radius must be equal to half of it. So the radius, so we define the radius R, we define R as the radius of this green semicircle, so the radius must be equal to half of the diameter. So the radius must be equal to the diameter AP over 2. And AP is equal to 30, therefore square root of 30 over 2 is the radius of this green semicircle. So the radius of the green semicircle R equals to the square root of 30 over 2. And the area of the green semicircle equals to the area of the circle over 2. The area of any circle is pi r square, and therefore the area of the semicircle must be equal to pi r square over 2. So write it down. The area of the green semicircle equals to the area of the green semicircle equals to pi r square over 2. R equals to the square root of 30 over 2. Therefore, the area of the green semicircle in total will be equal to pi r is equal to 30 over 2. Therefore, r square is equal to 30 over 2 squared divided by 2. So the area of the green semicircle in total equals to pi. We'll open the brackets here. Square root of 30 square is 30 over 2 square. 2 square is 4. So square root of 30 over 2 square equals to 30 over 4 divided by 2. 30 pi over 4 over 2 is 30 pi over 2 times 4. So here we have 30 over 2 is 15. Therefore, this expression in total equals to 15 pi over 4 square units. 15 over 4 is 3.75. Therefore, this expression equals to 3.75 pi. 3.75 pi equals to 11.78 square units. Repeat again, we actually found out that according to the second method, the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, the area of this green semicircle equals to 11.78 square units. So in the next step, I will summarize the lecture. We start with the first method, of course. In this lecture, we found out the area of this green semicircle using two different methods. So, in the first method, here we have two semicircles, and we know that this is line segment AC, this is equals to 5 units in its length. This is line segment CB, this is equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So in the first step, we joined points P and B together by a straight line. And then I copied the white semicircle in a new page, and we implemented the all 7 on the white semicircle. Actually, this is the white semicircle that I copied from the original domain. By joining points P and B together by a straight line, we created peripheral angle APB. This is peripheral angle APB, and it's subtended on AB, that is the diameter of this semicircle, and therefore, according to rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in its size. Therefore, this peripheral angle APB equals to 90 degrees in its size according to rule 7. Likewise, we joined points P and C together by a straight line, and then I copied the green semicircle in the new page, and again we implemented rule 7 on the green semicircle. So this is the green semicircle that I copied from the original drawing. Again, by joining points P and C together by a straight line, we created peripheral angle ACP. This is peripheral angle ACP. that is subtended on AP, that is the diameter of this green semicircle, and according to rule 7, any peripheral that is subtended on the diameter of the circle must be equal to 90 degrees in its size. Therefore, this peripheral ACP must be equal to 90 degrees in its size. Okay, so in the next step, I copied the two right triangles. This, the right triangle APB, and this right green triangle APC in a new page, and we proved that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles that are coming from the original drawing, and I proved that those two right triangles are similar to each other according to angle similarity rule. First of all, this is angle A, that is a common angle. It belongs to both triangles. It belongs to the green triangle APC, you can see it from the drawing clearly. And this angle A is also belongs to the right triangle APB. Therefore, angle A is a common angle that belongs to both triangles. Okay? So we define the common angle A is alpha, and therefore in this right triangle APB, this angle equals to alpha. This angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in any triangle. Likewise, this is the green triangle APC. This is angle alpha, that is a common angle, it belongs also to this triangle. So this angle is alpha, this angle equals to 90 degrees, and therefore the missing angle must be equal to 90 degrees minus alpha. In the next step, we proved that those two right triangles are similar to each other according to angle rule. So, I repeat again of the proof why those two right triangles are similar to each other. First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I actually proved that all the angles in the right green triangle APC, this green right triangle APC, are correspondingly equal to all the angles of the right triangle APB. Therefore, those two right triangles are similar to each other according to angle similarity rule. And again, I shall prove that the green right triangle APC is similar to the right triangle APB according to angle similarity rule. And for the fact that the two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AC in the green triangle over side AP in the white triangle equals to side AP in the green triangle over side AB in the white triangle. I repeat again. We derive that AC over AP equals to AP over AB. AC equals to 5. AP is the missing side, and AB equals to 6. So in total, we found out again AC is 5, AB is 6. Therefore, in total, this equation equals to 5 over AP equals to AP over 6. Here, of course, multiply this equation, and finally found out that 5 times 6 is 30, and 30 equals to AP squared. Here we took out of this equation and finally found out that the missing side AP equals to the square root of 30 units in its length. AP, it is actually the diameter of this green semicircle. So we found out that the diameter AP equals to the square root of 30 units in its length, and the radius must be equal to half of it. The radius is AP over 2. Again, the diameter AP is square root of 30, therefore the radius is AP over 2. AP is square root of 30, therefore the radius is square root of 30 over 2. So actually found out the radius of this green semicircle equals to square root of 30 over 2, and the area of this green semicircle equals to the area of the circle that is pi r square over 2. Again, the area of the green semicircle equals to pi r square over 2. So it is pi, r is equal to 30 over 2, therefore r square is equal to 30 over 2 squared divided by 2. We open the brackets here and found out actually that it is equal to pi, and square root of 30 square is 30 over 2 square, that is 4, divided by 2. So 2 will move to the denominator here. So in conclusion, we actually found out that the area of the semicircle equals to 30 pi over 2 times 4. 30 over 2 is 15, so in total this expression equals to 15 pi over 4 square units. 15 over 4 is 3.75, therefore in total this expression equals to 3.75 pi square units. In terms of numbers, it is 11.78 square units. I'll repeat again, in conclusion, we found out that the area of this green semicircle equals to either 3.70 pi square units, or in terms of numbers, it is equals to 11.78 square units. We finished with the first method. In the next step, I presented to you how to find out the area of this green semicircle according to the second method. In the second method, we join points P and B together by a straight line, and then I copied the white semicircle in a new page, and we implemented the rule 7 on the white semicircle after we joined points P and B together by a straight line. So okay, this is the white semicircle that I copied from the original drawing. We already found out that AB is the diameter of this semicircle in the first method, and here by joining points P and B together by a straight line, we created peripheral angle APB. Peripheral angle APB is subtended on AB, that is the diameter of this semicircle, and according to rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees. Therefore, this peripheral angle APB must be equal to 90 degrees in its size, according to rule 7. Okay, here line segment BP gets 90 degrees if PA, because this angle is a right angle. But PA is the diameter of the green semicircle. Here, PA is the diameter of the green semicircle, and therefore PO is the radius. So we define the radius of this green semicircle as R, therefore PO is R. Therefore PB or BP creates 90 degrees with the radius R. Again, BP creates 90 degrees with the radius PO R, the radius of the green semicircle R. Therefore, whenever you have a line segment that creates 90 degrees with the radius of a circle, you can implement rule 1. Repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So we have here line segment AB creates 90 degrees with the radius OM. The radius OM equals to R, it is the radius of this circle, and line segment AB creates 90 degrees with the radius MO. And because of the fact that line segment AB creates 90 degrees with the radius MO, it is defined as a tangent. AB is the tangent to the circle because it creates 90 degrees with the radius MO. So we can implement rule 1 in our drawing. Why? Because in our drawing we have here line segment BP. This is line segment BP, and this line segment BP creates 90 degrees with the radius PO. Again, line segment BP creates 90 degrees with the radius PO of this green semicircle. Okay, we know that angle APB equals to 90 degrees according to rule 7. Again, this is angle APB, that is a right angle. This is angle APB, that is a right angle. So line segment BP creates 90 degrees with the radius PO of this green semicircle. Whenever you have a line segment that creates 90 degrees with the radius, it must be defined as a tangent according to rule 1. And therefore, BP that creates 90 degrees with the radius PO must be a tangent. So BP is tangent to this green semicircle at point P. Okay? Again, BP is tangent to this green semicircle at point P. So here we have the common exam point B. From the common exam point B, we have tangent BP to this semicircle. And from the same common exam point B, we have here chord CA that was created by drawing a straight line from point B until it cuts the green circle, the green semicircle at 2 points, C and A. So we have from the common exam point B, we have tangent BP, and we have also chord CA that was created by drawing a straight line from the same common exam point B. So in this drawing, we can implement rule 10. Repeat quickly on rule 10. According to rule 10 is true in any circle. So in any circle, if AB is any chord in the circle and PT is a tangent to the circle, then the following equation will be true. That PT square equals to PA times PB. Again, PT square equals to PA times PB. We can definitely implement rule 10 in our drawing. Why? Because in our drawing, we have, from the common exam point B, we have tangent BP to this green semicircle, and we also have chord AC that was created by drawing a straight line from the same common exam point B. Therefore, all the requirements of rule 10 are satisfied, and therefore we can implement in this drawing rule 10. According to rule 10, we get that BP square equals to BC times BA. Again, BP square equals to BC times BA. Repeat again. According to rule 10, here BP square equals to BC times BA. Repeat again. According to rule 10, BP square equals to BC times BA. BP is the missing tangent, so we leave it as it is. So BP square equals to BC. BC is 1, therefore we substitute BC by 1. Okay, we substitute BC by 1. And BA in total equals to 5 plus 1, that is 6. So we substitute BA by 6. Here we substitute BA by 6 and BC by 1. So in total BP square equals to 1 times 6, that is 6. BP square equals to 6. We took a root out of this equation and finally found out that the missing tangent BP equals to the square root of 6 units in its length. This is the missing tangent BP. This is equals to the square root of 6 units in its length. In the next step, I copied the right triangle APB in a new page and implemented the Pythagoras theorem on this right triangle APB in order to find out the missing side AP. So actually, this is the right triangle APB that I copied from the original drawing. We already found out that tangent PB equals to the square root of 6 units in its length. AB is 5 plus 1, that is 6. and AP is the only missing side here. Therefore, we can implement here the Pythagoras theorem. Here by PT is the information for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle APB is AB, therefore the square of the hypotenuse is AB square, and AB square must be equal to PA square plus PB square. Again, AB square equals to PA square or AP square plus PB square. AB is 6, therefore AB square is 6. But before that, we subtract PB square from this equation and finally found out that AP square, that is the missing side, equals to AB square minus PB square. Okay? So AP square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, minus PB square. PB is square root of 6, therefore PB square is square root of 6 squared, that is 6. So in total, we shall find out that AP square equals to 36 minus 6, that is 30. AP square equals to 30. We took out of this equation and finally found out that the missing side AP equals to the square root of 30 units in its length. Okay. AP equals to the square root of 30 units in its length. AP is the diameter of this great semicircle. If the diameter AB is square root of 30, it means that the radius must be equal to half of it, that is AP over 2. AP over 2 is square root of 30 over 2. So actually found out that the radius of this great semicircle equals to the square root of 30 over 2. And the area of this semicircle, therefore, must be equal to, again, the radius is the diameter over 2. This is AP over 2. AP is square root of 30, and square root of 30 over 2 is the radius R. And the area of the green semicircle must be equal to the area of the circle, that is pi r square over 2. Again, the area of the green semicircle must be equal to the area of the circle, that is pi r square over 2. So the area of the green semicircle equals to pi times r square. R is square root of 30 over 2, therefore r square is square root of 30 over 2 squared divided by 2. We open the brackets here. Actually found out that the area of the green semicircle equals to here pi square root of 30 squared is 30 over 2 squared is 4, and 30 pi over 4 over 2 is 30 pi over 4 times 2, because 2 will move to the denominator here. So in total, we found out that the area of the green semicircle equals to 30 pi over 2 times 4. Here 30 over 2 is 15, therefore in total this expression equals to 15 pi over 4 square units. So actually found out that the area of this green semicircle, according to the second method, equals to either here 13 over 4 is 7.75, therefore in total this expression equals to 3.75 pi square units. So the area of this green semicircle, according to the second method, equals to either 3.75 pi square units. In terms of numbers, the area of this green semicircle equals to 11.78 square units. So in both methods, we arrived to the same result. Okay, thank you very much.